So on the previous lesson, we detected that we had kind of a row point here, and we want our system to be pretty robust. So it makes sense for us to account for the possibility of having some stray points and just eliminating them. Now, the way we're going to do this is we're first going to figure out what's the average distance between these points. We already know, according to the data from Open Topography, that we have an average of around 2.4 points per square meter, but that might also change depending on the data that we're downloading. So we don't want to just trust on the number that Open Topography gives us. We want us to be have a system that's going to figure that out by itself. So what we're going to do is we're going to write some code. We're going to create an attribute wrangle that's going to run only once. It's going to be a detail attribute wrangle, detail wrangle. Okay. And what we're going to do is we're not going to go over all the points. We don't need to. We just need a good number to use as a sample. Okay. We're going to run over a pre-established number of points out of our terrain, and based on that sample we'll have a pretty good average. We don't need to go crazy and just go over all the points. We can go through a percentage of those points. So let's figure out how many points we have to start. So we can establish that. Let's create an integer variable, and let's say total points. And the way we're gonna get this is by using endpoints, the number of points from input 0. If instead of using a variable, I actually connect this to an attribute, we should be able to see it here. So the total points coming in is this number, which matches that number. Okay, around close to 20 million points. So now we have the total number of points. We can, let's keep this just a variable, and we can just create another variable based on that one, which is going to be the considered points or the sample points. Sample points. It's going to be equal to a percentage of that. So let's say it's an integer as well. It's best to convert it. We're going to be kind of using a percentage. So it's going to be an integer total points, total PTs times 0.01. So we'll use 1% as a sample. Now we're going to run a for loop, and the for loop works basically on an initial state, and it's going to iterate over a variable, in this case I equals 0. Then it's going to continue while a certain condition isn't met. So let's say while I is smaller than our sample points. Let's keep this more readable. And at each iteration, the change that's going to happen is we're going to increase our I variable by 1. Okay. Now what's going to happen inside this for loop is that we're going to start by picking a random point. Rand pt is going to be equal to rand. We'll use the I variable as a seed for this random, and we'll multiply this by the total points. So this is going to give us, we need to convert this back to an integer, and this is going to give us a random point or a random ID point number that goes from 0 up to the total number of points. Okay, now we have our random point number. Now let's figure out what's the position of that random point number. create a vector. Let's call my pause. It's going to be equal to point. We're going to be looking at our input 0, of course, and we want to know the position. So the attribute is p of our random pt. Okay, so we have a random point and the position of that random point. Now let's figure out what are the neighbors. What's the closest neighbor to our random point? And for that, we're going to use a near points expression. That's going to give us a list of points. And we need to create a variable called my neighbors. Let's keep nays. Since this is going to return a list, we need to use these brackets. Now let's call near points from 0. We'll give it a position to figure out what are the near points. You can place the cursor over the function and just press F1. And this is the best way for you to learn about new expression. So we need to give it a geometry, a position, a maximum distance, and a maximum points. In this case, I just need 1. So the position we're going to be using is my pause. The maximum distance, let's keep it pretty far. And the maximum number of points, I just want to know the closest one. So I'm going to put 2. Now this demands requires a bit of explaining. What happens is that when you use this function on the same geometry input that you're running the code over, it's going to actually return the point, the first point that you're using as a lookup source. So the first point is going to be your point. So that's why we set this to 2, because we actually want to know not what our point is, but what the nearest point is. So that's why it goes up to 2. So the list is going to be composed of our point plus the closest point to our point. And that's it. So now if we actually found a neighbor, let's say if the length of my nays is equal to 2, then we'll measure the distance from one to the other. So if the length of this list is equal to 2, meaning that we did found a neighbor point within this distance, we'll most likely do find. We'll figure out what's the position of that neighbor point. So we'll go to vector. Let's call nay pause. It's going to be equal to point. Same thing. It's the 0 input, and we want to figure out the position. And the point now is going to be the second point, the second member of this list. So my nays 1. So the first one is 0 and the second one is 1. Now we have the position of our neighbor. Let's measure the distance between our point's position and our neighbor's position. And for that, we'll need a float to store this value. Let's call this my dist equals distance between nay pause and my pause. And we'll accumulate this distance on a variable called total distance that we can set to 0 right here. So float total dist, let's say it's 0, equals to 0, and we'll add my dist to the total list. So total list, total dist plus equals my dist. So we're going to be accumulating the distances, and when we're through going over all the sample points that we elected, we're just going to divide this number, the total dist, by the sample points, and this is going to give us the average. So let's gonna establish a float attribute called average. This is gonna be equal to total dist over sample points. So now we have our value here, and it pretty much matches the indication that we had from Open Topography, where it said that we had 2.4 points per every square meter. And yeah, if we consider this value, it pretty much matches that.